All right, before we begin, I'm just going to swivel this over here, and I'm assuming all of you can see exactly what's there. Let's see, can I actually? Ooh, I can. There we go. That is the schedule. Let's see if I can point to it somewhere. There we go.
So what was the thing next to the 27th?
There. Next to the relativity.
Relativity.
Yeah.
Oh, are we not writing the multiple choice?
Oh, yes, we need to do that at some point. I would have remembered that one.
Did you grade this test?
Yes, I have. You want it back tonight or Thursday?
Tonight.
Okay. Since you didn't get your way on the other one, we'll let you have this one. Multiple choice on the 27th? Actually, it might make sense to do that one sooner. I might shift the multiple choice earlier, just because of the material. Because by the time we're at the 27th, we're doing relativity or potentially quantum. And that stuff's not on the multiple choice test. So
So do we have one more test or two?
officially 2 more tests. There's the multiple choice test, and then there's the, got your calculator out. Or slide rule, or whatever you happen to be using.
Dr. Fox, will we still have material to discuss on the 27th?
Yes.
Because I was just asking because I'm getting my second dose on the 29th, and I was wondering if I could take the test earlier.
All right, well, let's talk about that separately. So you're putting your health potentially above physics. That's what I understand. See, this is the trouble with people who are going to pursue biology. Did Curie put her health above physics when she was exposing herself to radiation poisoning?
She would have if she knew the risks.
I suspect at some point she did know the risks.
Yeah. She probably should have noticed.
I would hope so. I think she was brilliant enough. Well, it's actually possible that she was brilliant enough that she was completely oblivious to such mundane things. And I'm sure I've talked about it before, but I still wonder about, because Curie got the Nobel, her daughter got the Nobel, her granddaughter, no, just a PhD. Just wondering about the pressure facing that third generation. Or Bragg in physics, there were 2 generations of Nobel Prize winners there. All right, any questions before I hit a couple of miscellaneous topics that we skipped and then pick up sort of where we almost had time to do last time? All right. This is a wire, by the way.
Is this chapter 32?
This officially falls into, I was thinking it was 31. This, I went back and I took a gander at the stuff that I missed. Seeing it right off the bat, it might actually be chapter 30. Yeah, officially it's chapter 30. So I have a magnetic field, obviously, out of the board, or I hope that you recognize the dots. and I have a current running this way. So the big question was, what exactly is carrying the current? Because it was originally designed thinking that there's this positive fluid that's flowing in the direction of the current. That was Ben Franklin's idea. And we sort of kept up with it, but there's really no way to test it of if there's a positive charge going this way or a negative charge going that way. And then Hall came up with a way of actually testing it. So let's just imagine it is indeed a positive charge traveling up. What would be the direction of the force on that positive charge? Right hand.
Towards the right.
So this side over here?
Yeah, and it curves radially outwards.
Right. Anyone else have a different hand gesture? Or you just trust Mario implicitly, except when he suggests 2 quizzes. All right, we got the stem gun. We have the current, or the positive charge going this way. The magnetic field is coming out. The thumb points in the direction of the force. So it will indeed be forced over to the right. So if it's a positive charge flowing in the direction of current, then the positive charge is going to be pulled over there. If it's traveling fast enough, it's not going to, smack into the wall. If I have a negative charge instead, which way will the electron be forced?
I would imagine in the opposite direction.
So you're going over left side.
Towards the left.
2 people moving to the left. All right, when you did the right hand rule, you did your, how'd you do it? Or you just went straight with, it's the opposite. Did you right hand rule or?
Q equals V cross B. B is out of the page. I had J dash positive.
All right, so if we've got,
The Q is a negative.
that my velocity is in the negative j hat direction, if we're doing it that way. The magnetic field is in the k hat direction. Q is a negative. J cross k is I, so that becomes negative I, negative or positive I hat. It will be forced over here. Now, your idea of the opposite, recognize we have 2 different opposites that cancel each other out.
Right.
One's going to the other direction, and also it's a negative charge.
Yeah, I forgot.
So the electron would be forced over to the right side as well. So if we expose this wire to a magnetic field, then either I'm going to have an abundance of positive charges on this side, if it's the positive charge flowing, or I have an abundance of negative charges on this side. So theoretically, I just hook this up to a voltmeter. And I see which side is positive, which side is negative. Now, the actual mechanics of it are far more sophisticated than that, and it tends to be the one that I looked for it. I think the shape was something like that they were shooting the current through. But I just wanted to get in at least the concept of the Hall effect. All right, questions about the concept of the Hall effect and how it actually finally identified that it's the negative charges flowing. All right. Does inquiring minds want to know? This next bit will be from chapter 31. Okay, chapter 31. So what I have here are just normal little magnets that I have picked up from Home Depot or Lowe's, one of the two. Just ordinary magnets. There's no glue on them, there's just magnets stuck together. This is an ordinary copper pipe. Copper is not a magnetic material, and I can show that easily enough just by the fact that the magnet is not sticking to the pipe. Now, just to give you some sense of speed here, I'm going to take an ordinary marker, and I'm just going to drop it through the tube, and have some sense of how much time it takes to get to the bottom. Now I'm going to take these magnets, and I'm going to put the magnets through them, and fortunately they fit quite nicely. Same, longer, shorter.
Longer.
Okay? Oh, so the question's coming up, why? And now I take a more powerful magnet. And get it off. And this is a more powerful magnet that I'm now going to drop through the tube. I think that is clearly even longer. Or if I put two of them together and I dropped it through it. Well, let's do it. They came together to pinch my skin. Did not want that to happen. This is easier than I thought. All right, so why? What's happening to cause these magnets to travel slower through a non-magnetic material? Let's open up for anyone.
Thinking it has something to do with conducting through it.
Okay, keep going. Or you can just lob that out there for someone else to pick up.
Well, someone else would pick it up.
Okay, so it does have something to do with the conducting. I did not drop it through a piece of PVC pipe. I also did not use steel pipe. Steel is also a conductor. Steel would have been a horrible thing to use. So why would I not use steel? Say it again?
The magnet would stick to it.
Absolutely. All right, so back to what are the copper pipes conducting and not magnetic?
Is it because this is not a full answer? It's just is it because when as the magnet drops, that's like there's like moving charges, like an illusion, or
Moving charges.
or because the copper has like electrons,
Okay.
and then as it's like as the magnet moves, and then the electrons, it's like it creates an illusion of moving charge.
And then?
And then I'll allow you guys to.
Okay.
Really continue.
I think there's a stronger magnetic force. There's conducting electrons, because it's a conductor, that are free to move, like she said. The stronger the magnet, there's a stronger magnetic field, which creates a stronger force.
And then? Slowly piecing it together. There is a different approach to take other than the force on the electrons, but it's valid. So we have a force on electrons because there's a relative movement between the electrons and the magnet. Which way will the electrons be moved? Let me draw the copper pipe, oh, we got copper pipe right here. Get rid of this part. Oh, get rid of our magnetic field there. Just for the sake of this, we'll just assume north end, south end. It might have been the other way, I don't know. What would slow a magnet down?
I feel like it was, like moving around the inside of the pipe.
The magnet?
Yeah,
They go with the friction angle?
yeah.
If, I haven't actually done the official testing, but wherever I put them, the strong magnets over there are smoother than these are. And so friction would not affect them as much. And so, but those took a lot longer. So there's gotta be some, friction I suspect is an incredibly minor effect here, just because I can stick my finger in here and it's relatively smooth
Okay.
inside, so I don't, unless there's a huge rough patch in the middle, I don't think friction is a significant impact.
Okay.
Marisol, you keep looking like you want to say something.
So do the electrons just build up on the north end of the magnet, kind of like holding it back, making it take longer?
How do the electrons hold it back?
They flow towards the north end of the magnet.
All right, take the essence of her idea, not the direction, but the essence of her
Oh,
idea.
towards the south end, sorry.
Still take the essence of what she said, not the direction. Combine it with other things people have said.
Can you repeat these?
So wherever the electrons are flowing, it's kind of creating like an opposing force to the magnet, holding it back from going faster. So I don't know if it,
So if it's like, if the force is supposed to be up, because we're slowing it down, then it's supposed to be V cross V or something?
I missed the last part.
Then it's supposed to be V cross V,
Would
so
be
that's
going
not.
down. Which way is the magnetic
Or
field?
V cross V.
Magnetic field coming from this magnet would be,
so that's just slowing it down.
so what would slow this down?
Force going up?
Velocity.
All right, so more specifically, if I had another magnet, how could I slow, if I have a north pole coming at me, how could I slow it down?
Create another pole.
All right, which way would that, did somebody say monopole?
No.
No. Create
Alright.
another north pole.
A north pole, okay. So remember magnets have a north and south pole, so if I had a magnet here, which way would the north pole be facing?
Towards, yeah.
The
The top.
top, okay, and up here?
Would be the same, right?
North.
So the south could be attracted to the other side?
Yeah, but the south is closer, so this could have so I want the north pole
Yeah.
below it here and above it here. So my thumb is the north pole. All right, so how would the electrons move down here in order to do that?
In order to do.
In order to create a north pole here and a south pole here?
Would the electrons be moving away from it?
Oh, wait, this way?
Yeah.
Running Roman invasion. The cows move away. No, if they did that, that would create, so if the electrons flow that way, that means I have a current flowing that way, which would create that would create a magnetic field that's flowing, basically circling.
Towards the right.
The electron's flowing that way? Is that what you're saying?
The right,
To your left.
Oh, that right,
yeah,
okay.
sorry.
I've been doing this long enough, you think I'd learn by now, I think it's only gonna get worse, but alright. So the electrons are moving that way, you're suggesting.
Mhm.
So if the electrons are flowing that way, that's like there's a current flowing that way.
Mhm.
So if the current's flowing that way, then that would create a magnetic field that is going in there and out here. Sort of going like that.
Into the page?
Into
That way? If you're doing that way, if electrons are flowing that way, that means the current's flowing that way, which would create a magnetic field that would go, sort of like that. People are dancing around it, I think the only thing that's left is the right solution.
That would help.
So if I have electrons flowing in one direction, let's just look at it from that point of view. So if I have a line of current here, tell me about the magnetic field that's created by that current.
on the top of the page and on the bottom out.
All right,
Wait, would you need two, like, flows of current? Would you need like two flows of current?
oh, to sort of balance out something here?
Yeah, cause it seems like there's like two from the north and the south from the magnet.
Well, there's two, so John, it's actually 360 degrees all the way around this way. So first off, in a one direction like this is not gonna cut it. So what's our alternative? And this might get sort of what you were saying.
Like, yeah, like two paths of current.
Except be careful, I mean, as we did from chapter 29, if I have two currents flowing in sort of in opposite directions like that, so
They would repel.
they would sort of cancel each other.
It'd be infinite number.
I'm sure from a physics point of view, we can always on a board come up with an infinity somewhere, but what did you mean by that?
So if no, it wouldn't work. It would cancel everything out.
Does it have to do with the shape of a circle since it's so similar?
Say it again?
Does it have to do with the shape of a circle since it's so similar?
All right, so what circle do we, so it has something to do with the shape of the circle. Which way is the current flowing?
Oh, around the.
Yes. The current's either gonna be flowing around like that or flowing around like that. The current's gonna be circling the pipe.
And it goes into the page.
So if the current is flowing around, I guess from an overhead point of view, counterclockwise, then the North Pole is gonna be up. If it's flowing the other way, the North Pole will be down. And so what we have here is I have a current flowing. That is just horrible. So it's going, the current is flowing this way, that way, and then that's my attempt to say the current's flowing around like that. And up here, it's flowing the other way. I'm assuming in your own notes, it'll be drawn perfectly. So the electrons are flowing in the opposite direction, this direction of the current. Known in fancy circles as a Lenz's law demonstrator. Or I plot the pipe that Home Depot or Lowe's. In the magnets at Home Depot or Lowe's. And you can amaze your friends and family with a copper pipe and magnets. And I fortunately bought that copper pipe before the prices went way up too high. so that's the copper pipe. All right, I'm now gonna jump to chapter 34, I believe it is. Questions before I actually drive the speed of light? And I will leave room for this. All right, so we have the four major equations dealing with electricity and magnetism or electromagnetism. At this point here today, known as Maxwell's equations. We have the electric flux through a closed surface is equal to the enclosed charge divided by epsilon sub naught, assuming free space. We have the magnetic field dot dA is equal to 0. So the magnetic flux through any closed surface is 0 because there are no monopoles as far as we're concerned. And then we have the two that are crucial. We have the line integral of the magnetic field around some loop is equal to mu naught I plus mu naught epsilon sub naught times the time derivative of the electric flux. And then, so this is Gauss' law or Gauss's law, depends on if you put the X or S or not. This is Ampere's law. Apologies to the family for by having listing an accent mark with Maxwell correction. And then the line integral of the electric field around a closed loop, that basically is a voltage, that's equal to the negative change in the magnetic flux. And this is known as Faraday's law, but I like to give Lenz credit as well. Faraday and Lenz's law. So that's where we sort of, when we get to that point, we can now derive the speed of light. However, we do need to do a little quick review of math. I have some function p, which is equal to the sine of q. Typical sine function. What is the period?
1. 2 pi.
Anyone have a different answer? Does anyone have the same answer? You feeling like this is a trick? All right, so you said 2 pi. How'd you get that?
Sine.
Okay.
Pi.
What's that?
Is it pi?
No, 2 pi is gonna be closer. All right. Usually there's more response and agreement with that.
I guess it's just like, I don't know, that's just how I think of sine. It goes from 0, pi over 2 to 2 pi.
Doesn't go no more.
That's a full cycle.
Yep, so my amplitude here is 1, that's -1, and if you go around the circle, how many radians in a circle?
2 pi.
Okay, all right, we're in agreement on that one. So the period, I asked what's the period, he said 2 pi.
Yeah, 'cause that's
Anyone want to
like 2
disagree?
pi's over a circle.
Oh, wait, how do you, is it 1 over 2 pi? Is it 1 over the frequency?
T is 1 over the frequency, but no, your thinking was right to start with. Why I'm being hesitant here is about to come up. Austin, you said something?
Nothing important.
Okay. All right. What's the wavelength?
Is that just the amplitude?
No, that amplitude would be the amplitude. Amplitude in this case is 1. That's 2 pi right there. That's pi. That's pi over 2. That's 3 pi over 2. It takes 2 pi before it starts over again. Is that the period or is that the wavelength? Why not the period? And you know, if you had said period just then, I would have said, why not the wavelength? So,
The period is the time it takes, for one full cycle
and wavelength?
of the length of the entire cycle without respect to time.
Okay, so how do you know that this is you said, both said wavelength and not period?
Yeah, wavelength.
Why? Is it period and not wavelength?
Why is it period and not wavelength? Or-
Sorry, why is it wavelength not period?
Because it's not with respect to time.
It's with respect to distance?
I guess it's with respect to Q.
Ah, what's Q?
Charge.
Oh,
No,
no,
I don't know what Q is.
not in this particular case. That would be a bizarre math formula if this was charged. It is actually impossible to know what the wavelength or the period is. Something is 2 pi, but we did not give you enough information. Is Q a quantity of time or is it a quantity of length? Now, I was thinking back when I was first dealing with this from a teaching point of view, and I was flashing back to when I was taking math classes and going, did they ever differentiate? Generally, they said, what's the period? And I did that coefficient here, 2 pi divided by that coefficient, and that was the period. They said, what's the wavelength? I did 2 pi divided by whatever the coefficient here is, and that was the wavelength. I don't think they ever mixed wavelength and period in the same problem.